Great.
All right. So my project is called BalanceBite, and my main goal for this project is to understand how stress triggers can be improved using personalized food recommendations and then like prevent emotional eating incidents. So my main goal came from the fact that there are a lot of food journaling apps out there, but then there is nothing that is personalized to you, like as a user. So it's very mass produced and then very static in terms of just, being very rigid with the structuring of the inputs from the user and then storing the user logs and then stuff like that. So I thought maybe because the LLM is really good at understanding the context of the note. So this is exactly why I came up with BalanceBite. So today I'll be discussing the problem, the data collection and pipelines, and the LLM context layer, and then the recommendation engine, and how I'm evaluating and testing my model. So the problem is to predict and intervene before emotional eating happens. That is, even before anything happens. So let's say you log in something like, oh, I'm stressed today, and then your last meal was at 5 a.m. in the morning. So by the time it's 6 p.m., the model will be able to understand that you are prone to eating, overeating, or like you're at the borderline of, like stress eating or emotional eating. And when people with emotional eating disorders, me included, so they are more prone and they're more biased to um, seeing this kind of structures. So that is exactly why I'm using LLMs as a contextual reasoning agent. So both the structured data and the unstructured data can be logged in, such as mood nodes, stress causes, or time context. And yeah, this is the architecture I'm going with. So I kept it very simple for the MVP. So the first one is the data layer. It contains all the stress triggers, meal logs, emotional tags, time context, which is really important. And then there is a feature encoding where I normalize all the structured and unstructured data into numerical numerical points, and then I feed that into the LLM context builder. So it takes all the numerical data and the instructions and builds out a JSON format where that could be fed into the recommendation layer for with the probability of emotional eating, and then it gives out any suggestions such as food aware, I mean healthy food options or like behavioral options such as walking, swimming, etc. Because during my research, I found out that women are more prone to eating, overeating or like emotional eating than men. And then a lot of men prefer, just like if they're stressed, just go for a walk at the like just like hang out with friends and stuff like that. And I saw this as a behavioral pattern amongst the genders. So that is exactly why I'm using context aware recommendations. And obviously I need a feedback loop for this project to understand the user better. And then I reinforce the model using rewards and then generate weekly dashboards and feed that into understanding if the model is actually working. So this is the data layer, and I am building the app for this one. So I'm collecting all kinds of data about the user. So there is a survey before the user logs into the system. So that helps me to understand the user even before he or I mean they have joined the app. So that helps me to build off on cold approach to the user. So I have once they log in, there is mood logs, there is behavioral events such as mealtime or food preferences or the size of portions they've had. This is to actually detect the temporal eating patterns. And then there is environmental context, such as any seasonal or cyclic biases. So if, let's say every Sunday I feel like having an ice cream. So that bias triggers me every Sunday to, just go have an ice cream, even if I don't feel like it. So there are biases associated with the users. So this is exactly why I'm feeding that into the system as well. And then there are triggered tags such as like unknown events or like maybe boredom or like a social gathering. So all of this will be fed into the model using one hot encoding. And then I have a section for the notes where they can just write down whatever they feel. So this the about things are just like buttons. So you tap them and then you can just rate it. So it's very easy for the user to, like get through the journaling fast, but there is also a section they can personalize their day. So that is the notes section where they can type in whatever they've been going through the day, and then those notes will be used later on for the LLMs. And and then the outcome is if the user is prone to emotional eating later in the day or during the course of the day, and then what is the amount consumed, and then let's say they don't take any recommendations suggested by the model, and if that does not work for them, that would be fed again into the model itself, and that way it will be better as we go. And the data collects its the data sources are the app interface, and then this is a future scope, but I'm planning on like using passive sensors, more like wristbands or something like that. But that is something in the future. But for now, it's going to be app interfaces and then real-time data using like notifications or like recommendations accepted by the user. So that's the source of my data. And then I'm using feature encoding. This is the next step in the architecture. So everything collected here might be structured, unstructured, or semi-structured. So using feature encoding, I am going to be turning those into actionable insights. So converting those into vectors and then converting the unstructured features into embeddings. So let's say, for example, the user types in something like, I had a rough day at work and skipped lunch. So that will actually break down each of the text into tokens and then understand, associate each word with a sentiment. So it will use the model of Open API like text embedding, and then it generates the emotional tone and the response from the model. And then I'm using technical stacks such as pandas and numpys and all that to store the data into my tables and stuff. And I'm keeping it batch process data. So every few hours, let's say throughout the day, the user logs in once or maybe three times a day. So I want it to be real-time updated data so it performs better. So I'm using batch processing here. And then all of this data, when collected, goes into the LLM layer. Um, this goes, and then the input would be the encoded data. Let's say the stress level, the user rates it as 8 on a scale from 1 to 10. And then for the triggers, the user says something like the work pressure. And then the last meal might be, 6 hours or 10 hours ago, when the mood is anxious. These are all just like an example for you guys to understand. And then the context would be generated as something like this, that is more understandable by the LLM itself because it takes tokens as input. So it would generate something like user reports, stress 8 on 10 due to work pressure, and then the last meal was 6 hours ago, and the current mood was anxious, and typical behavior from the previous patterns will be stored. So something like emotional eating with, like they prefer high sugary foods or something like that, or they might prefer spicy food, depends on the user preference. So this will be fed into the data, and then there will be a prediction or a probability of, like how probable the user is to stress eat in the next 2 hours, and then suggest a preventive measure. So this screenshot you see at the bottom is the JSON that is capturing the essence of all the logs generated by the user. So you can see that each individual user profile is stored with the score, the daily score, and then the common triggers would be work pressure for someone, or it could be something like an emotional event happening in their life. And then they can log in how they feel throughout the day. And then that's how, like the instruction here is to estimate the emotional risk and then generate a personalized recommendation to prevent it. So this is fed into the LLM, and the LLM then generates a response for this and then feeds it into the recommendation system. So here,
Can
you
I
can
ask a
see,
question?
yes.
Is there what do you mean, I guess, here by emotional risk? Is there like a grounded notion of what
Yeah,
emotional
so
risk?
it's gonna calculate the probability of, like uh just like eating, like let's say they might stress eat, or they might go emotional eating period of some sort. So it just rates the user from the probability of like how probable are they to just like maybe stress eat or something like that. And if the score is higher than a threshold amount, it's going to generate a response. But if let's say they've had a good day and there's nothing much going on, so then that score would be lower on the end, like towards zero. So then they would just be like, oh yeah, you're fine, so keep enjoying something like that. So it does not generate a response there, just logs in the mood throughout the days of the week, something like that.
Hmm. Okay.
Yes. So the recommendations, this could all to- this whole project could also be done using random forest, but that would be a very, very static approach because it's very like binary, so either yes or a no. So I do not want that. So that is exactly why I'm using LLMs to feed into the recommendation system. So here the input would be the JSON file with the context block and the instructions, something like like going on a walk or something like that, and that would be based on contextual or like collaborative filtering methods. So the most popular recommendation that works for the most people would be given out for the whole users or the first time users, and then based on their feedback and based on whatever's working for them, it would get updated, and then there will be a feedback loop in between of all this process. So there is also a mechanism of chain of thought. So the first one would be to assess the hunger levels and then the time of the last meal, and then evaluate mood intensity from the score, the stress score, and then if there is any similar patterns in the past, and then overall score for the risk, and then given on 1 to 10, 0 to 1, it just generates response based on that. And then there is a feedback rating at the end of the journaling. So I am collecting the rating for the app itself, and then the rating for the recommendation, and then if the user is satisfied, and all of this will be fed back and matriculated on a weekly dashboard. So the user can also see the insights. And then at the end, this is how I'm evaluating my model. So let's say there are 6 incidents of emotional eating for user in a week, and then they have been using the app for a amount of time. And then coming 3 weeks, let's say there have only been two events. That suggests that the app has been successful in reducing their stress eating patterns. And then there is also mean caloric derivations from the baseline. So this is basically the amount of you know when a person is stressed, they might go for like high caloric foods that might not cater to their healthy lifestyle. So it takes a track of all those foods, and then it calculates, and then both of them will be fed into like a Z test to understand if there's like a reduction in the whole process. And this would be for 1 to 4 weeks, and then if there is a reduction, it continues with that, and if there's no reduction, then it goes back to the start, and then suggests different criteria or like methods to cope up with their emotional eating patterns. And yeah, that's it. Thank you. Let me know if you have any questions.
Uh, Thanks for the talk. Any questions from the audience? I think there's one in the chat, if you can see that.
Okay. Let me see. How do you distinguish from stress eating and non-stress eating during the meal? The since we have different set of parameters such as stress score or maybe like a mood overall. So let's say someone is bored and they might not be eating food based on just stress. That could be boredom. So let's say they log in their stress as one, and then they log in their mood as bored. That could be a non-stress eating event. So there are different parameters to exactly monitor what kind of eating pattern that is. So if let's say their stress and their mood is overall anxious, so it's gonna give a score out of 1 to 10 as 8 on stress scale, and then mood as anxious. So anxious itself is context aware word, so you can tell that the person is stressful, and then that is how their patterns can be identified, because we my project has different parameters. So there is stress score, there is mood score, and there is also a notes section. So all of the words that they mention in their logs will be used to understand if it's a stress pattern or if it's just a boredom, or like like, oh, I have nothing to do today, so I might just like eat, or like I have nothing to, let's say they're not sleeping. So that could also be one of the cases of overeating. So that is exactly why it's not linear dimensional. It's like dimensions are there. So it handles everything. Yes. So, yeah, I have read a lot of papers on this. Most of the papers are for addictions, and this is a really good use case for addictions as well. But I am currently focusing on the food itself because a lot of my friends who've been using the app feel it's really, like help them. It's like a small number of people, but the recommendations are good. So if it can be scaled to more users, then yeah, absolutely. Like addictions can also be tackled in the similar way.
Yeah,
Which
maybe.
part of the app or the process do you want to work on next? Like what are your next steps?
I initially built the app on React Native, so I'm working on creating like a friendly UI UX design for the user to use it more. So,
Mm.
I mean, the backend is all set. It's able to, like generate responses and stuff. But I'm working on the front end, like making sure the user, wants to log in, and then working on like a reward system for the user themselves. So something like points or like like a leaderboard, something that makes them come back and use it more often because most often than not it's always a back thought for a lot of people to log in or like journal in general, so not a lot of people like to journal, so I
Mm.
want to make it like a conscious effort from the user itself, so they want to come back to the app, so that's what I'm working on right now.
Cool. Any other questions?
Yeah, I'm also working on like recommendations. I found this really cool API that has like information on, let's say someone is craving for candy, so that could be, like a kind of deficiency that they might have internally. So like magnesium deficiencies or stuff like that. So if you have food with higher magnesium content, it is known to reduce your chocolate cravings. It happens for a lot of women around menstrual time. So for women users, I'm also working on like having a specific category for, like their menstrual cycle. So that also can be implemented in the later stages. So yeah, something like this could be also a really good addition. Thank you. Thank you, Chetan, for saying that.
All right. Well, thanks for the talk. Cool project. Hope to see more
Thank
in
you.
the future.
Thank
Next
you.
up, we have Mohammed presenting
Yes,
update on Weight Watcher federated learning. Of
yes, sure. Thank you so much for accepting my late request.
course.
So I'm going to share my screen. Okay, do you see?
Yeah.
Okay, good. Okay. Hi, everybody. Welcome to my presentation. My name is Mohammed. I am a PhD candidate in University of California, Merced. I'm working with Professor Yang Chen and Roman Marcia on federated learning and differential privacy. Today, I'm going to tell you about the weight watcher with federated learning. In fact, I'm going to use a tool called a weight watcher for improving federated learning. Uh, okay, first, we have an introduction to the federated learning. Then I will show you what is or what are the challenges in federated learning. After that, we see the research question, and next we have proposed algorithm and experimental results and summary. So first we need to know what is federated learning and why do we need federated learning. Uh, so in traditional learning, we had to gather all of the data in a central server to train a model. In fact, in this case, we don't have any privacy because we had to share our data. Okay, but in federated learning, every client, suppose we have K clients. Okay, every client trains its model locally and just shares the update to the central server. And the central server does the global aggregation and returns the new global update to the clients. And by doing this and repeating this process, we get a target accuracy. So here you see that by doing the local training, we are not sharing the raw data to the central, so we have privacy. That's the main advantage of federated learning compared to the uh, traditional learning. In fact, here you see that. So in local training, we have an optimizer, for example, SGD. Each client does the training and just sends the updates to the global center. So uh, in other view here, you see that we have a central server here. Okay, so we have 4 clients. Okay, every client does the local training and sends the updated model to the server, and server does the aggregation, and after doing the aggregation, it sends the global model to the clients. Okay, so this process can be done for uh, for different reputations. So here you see that the clients just sends the updated model and doesn't share the data. So, but there is a challenge here in federated learning. Some clients shares for example, unreliable updates. Okay, that those updates may skew the global model. Okay, so here, although the federated learning is a privacy preserving AI tool, but outlier updates caused by having different data sets or noise or malicious behavior can derail the model performance. So the question here is that how can we mitigate this impact? Okay, so we have a solution called weight watcher federated learning to address this challenge by reducing the influence of malicious client updates. Uh, to our knowledge, this is the first time of using weight watcher for improving federated learning. So we have here federated averaging learning, or called FedAVG, introduced by McMahon. In fact, suppose we have a global model. We are minimizing this function f is summation of nk over n times capital Fk. So capital Fk is the loss function of the each client. Okay, and nk is the size of data for each client. So here we have a local client update at round t using SGD. Other optimizers can also be used, and also we have aggregation process here for global server as follows. Here you see. So so what is the idea? The idea here is improving federated averaging learning using weight watcher based on FedAVG. Okay. In fact, the novelty here is that we use power law-based spectral analysis to detect outliers. Okay. So the key steps here, we have a spectral analysis, then we have a temporal change detection, and after that, and at the end, we have weighted aggregation. So here, there's a theory called heavy tail self-regularization. It says that well-trained neural networks show heavy-tailed eigenvalue spectra in weight correlation metrics, okay, introduced by Dr. Martin, which is published by this paper. So, in fact, we can say that well-trained neural networks have heavy-tailed behavior that can be modeled or fit by power law distribution. So in real world neural network, you see that the singular values or eigenvalues of a weight matrix for a specific layer in that neural network doesn't follow a simple Gaussian distribution. Okay, so in fact, we need a tool to model that behavior. In fact, the best idea can be power law to quantify this behavior. This behavior can be called as heavy tailed. What is heavy tailed? In fact, in heavy tail, you see that a small number of large eigenvalues, and we have a line tail of many small ones. So experiments done by Dr. Martin says that the power law exponent is the key indicator. In fact, it says us about something about the healthy of the model. So, uh, and the base range for the exponent, this exponent is a constant, okay? This exponent should be something between 2 and 6 to say that here, yeah, our model is well trained, okay? So the examples of well-trained models are something like ResNest and GPT-2, and the poorly trained models reported by Dr. Martin is GPT-1 or GPT. Okay, so based on these experiments, we rely on these experiments, and we use this indicator, power law indicator, to improve federated averaging learning. So, um, so how to use power law for improving federated averaging learning? So for each client K, we use a specific layer of the weight matrix. After that, we compute the correlation matrix of that weight matrix. Okay. After finding the correlation matrix, we calculate the eigenvalues of the correlation matrix and also we do analyze on the empirical spectral density. In fact, that is the histogram of eigenvalues. Okay, so after finding the histogram of the spectra or SED, okay, ESD, sorry. So we model the ESD by using a power law distribution like this for each client at around T. Okay, K is for clients and T is for round. Okay. So after modeling the ESD as a power law distribution, we need to find the exponent alpha k t. There are some methods to find this exponent. So here we can use maximum likelihood estimation. So now, after finding this exponent, how to use this exponent for improving federated learning. Also here, there's a tool introduced by Professor Martin, and you can, in Python, you can use this tool to find the details about the exponent. Easily you can find these exponents by using this weight watcher tool. Also, so the key idea here is that after finding the exponent, okay, we track the changes of the power law for each client at around T. Okay, so for example, here we can compute the delta of alpha k at around T as follows here, and we can also consider a threshold delta if this change is larger than that threshold. So we flag that client as malicious, okay, or a client that sends the unreliable updates to the global server. Okay.
Hey, Mohammed, can I ask a question?
Yeah.
So this is based on the power law of the spectral density of the weights.
Yes.
In learning and in federated learning in particular, I guess the weight updates are fairly small. You're taking a small gradient step. Do we expect that the power law exponent will change with each gradient step only kind of, I guess, a very small amount? Is that how I should think about this?
Can you repeat your question? Sorry, it wasn't unclear for me.
Do we expect that the power law exponent will change a small amount when we take a single gradient step? Because the gradient step only changes the weights in general by a small amount. Does that correspond to also a small change in the exponent?
So we do this for every client, okay?
Right.
So also, in fact, if we want to do this every round, that would be computationally expensive, okay? So we can do it, for example, in every 5 round or every 6 rounds, okay, to less the computational cost. But yes, we need to to track this change. Yes,
Okay. And then you mentioned malicious clients. Is our primary goal here to detect like
exactly.
malicious federated learners? Yeah.
Yes, yes,
Okay.
yes. Sometimes some updates are very large or very small. Okay, so those very large updates to skew the global model. So we need to detect those updates and to mitigate the influence of those updates.
All right. Cool. Thanks.
Yes, sure. Also, we need to detect the irregular behavior of clients. Okay, how by finding the variance of the exponents. Okay, so for each client at round t, we find the variance, and the alpha t bar is the average spectral quality of all the clients of the active all clients. Okay. So if we see inconsistent behavior for the some clients, so we need to inject a scaling factor to reduce that influence. So in fact here, if the variance are very high, and also on the other hand, if the delta alpha k is larger than that delta, okay, so we reduce the influence of those malicious or unreliable or not well trained clients by this relation. Okay, so for healthy clients, we use kappa KT1, and for unreliable or not well trained clients, we reduce their influence by this. On the other hand, we inject another filter to assign a higher influence for clients that are healthy. Okay, so for the clients that the power exponent is between 2 and 6, we consider 1, and for those larger than 6 and less than 2, we reduce exponentially their influence in federated learning. So after doing this, we consider another constant calling nkt times h times kappa kt, which h is defined here above here, you see, and kappa t also is defined here. Okay, so and for the global model, we have a new update here. You see that here we are injecting the beta kt to the global model to assign a higher influence for the healthy clients and reducing the influence of unreliable clients. Okay, so in fact, we have a summary of here for data average learning algorithm here. So first we find the power law locally, okay, by clients who performs it by clients locally. The purpose is the extracting spectral quality, and then we send the power laws to the server. Where it happens, it's through communication. Also, who performs it? Here we can say that so client sends to the server. The sending is by the client. Okay. So the purpose is sharing compressed spectral information, and after that we are computing delta alpha k by a server, and also to detect the instability and the drift. And at the end, we compute the variance, and also we compute the scaling factor in server, and we do the aggregation rate uh, um, by the server. Okay, so we have experiments here. We have three data sets. We have a heart disease data sets, and also we do this experiment on a vehicle energy data set, and also on CFAR10 comparing with different algorithms. The evaluation metrics are test accuracy and mean absolute error. Uh, for the CIFAR dataset here, you see that we have higher test accuracy compared to the other algorithms such as FedUIN, DPFed AVG, FedPrax, and FedAVG. And here also you see that the average values of exponent for the 30 rounds. Okay, for the first one, you see that the exponent is 5, and the second one is around 6.1. And also you see that by uh, increasing the number of rounds, we have a decreasing trend for the power law exponents. For 4 clients, here you see that for the first round, all the clients are healthy. We don't need to remove none of them. For the second round, you see that one of them is healthy client, but 3 of them are not healthy. Okay, here you see that they are not well trained. For the third round, you see that only 2 of them are healthy or well-trained clients, but 2 of them are not healthy, and you see that the same for other. Also for
Mohammed, were you explicitly simulating malicious clients here? Like why are they unhealthy?
because they are not well-trained, their exponent is not between 2 and 6. Here we are detecting the unreliable clients.
How did you make them behave in an unreliable way? You just trained them less or something?
Yes, here, okay, here you see that. Here, by finding delta alpha k
No, I know how you're
and detecting
detecting it, but what did you do to these clients to make them unreliable?
okay, so the key point here is that, okay, if the if the if the
I
power
get how you're
exponent is
estimating,
I think
like,
probably they're
why are
just
they unreliable?
naturally less trained than others. Are they just all random and then some of them just less performative and you're catching those?
no. Here you see that. So when delta alpha k is larger than a threshold, okay, so we consider those on as unreliable uh, clients because they are not well trained based on this criteria. Okay, so
Yeah,
for
but how did
example,
you, in the experiment setup, did you first make a bunch of unreliable, like ground truth unreliable clients?
in the experiments, okay, so for the experiments, we need to find not well trained clients. Okay, we call them excluded clients. Okay, how? By using this here, by using this criteria. For example, suppose for the first round the exponent is, for example, 3. Okay, but for the second round the exponent is, for example, 90. Okay, 90 minus 3 is about 87. Okay, it's 87, so 87 is very large. Okay, so we can exclude that client from the aggregation, from the process. Is it
Good.
Makes
clear?
sense. Yeah. We're pretty over time. We're at 21 minutes now.
Okay,
Can
sorry.
we wrap up in maybe 1 minute
Yeah.
or so?
Okay, yeah, sure. So also for hard disease prediction for different batch sizes. So we have you here, you see that comparing to other algorithms, we see that. So we have higher test accuracy for heart disease prediction, and also for the energy consumption modeling of electric vehicle battery. Here you see that. So we have a lower mean absolute error compared to the other algorithms. And these are the references, and thank you so much for your attention.
Cool. Thanks for the talk. We are over time, so let's defer any questions to the chat. Feel free to ask Mohammad any questions there. Let's go on with the third talk, which is by Changqing on transformers as effective fields.
So thank you. Can you hear me?
Yep.
Yes.
Here.
Okay,
and
great. Great. So today I'm very honored and happy to talk here. And thank you so much for Jason and Rosanne for organizing this great event. And I am a very faithful audience of ML Collective. And today I signed up for this talk because I was recently wrapping up my PhD in Dauphine and PSL in Paris. And so I came across an idea, and I'm very, very curious about hearing other people's ideas. So I'm actually building an architecture theory of the transformer architecture. And as I said, this is from the physical law. And let's get started. So first, we talk about generated model, and there's a miracle happening in the training and in the inference. So we naturally ask what happened inside. So today's message is just one thing, is that transformer is not a mere engineering miracle or coincidence, but it is grounded in principles from physics, or especially quantum physics or theoretical physics. And today's goal, as I said, is that I find a lot of places, I did a lot of research, but I don't find a precise reference for these specific ideas. And after asking many people, so please correct me if I'm wrong and guide me to any existing papers. Thank you. And the plan is to talk about what the definition of transformers, and then a potential field. And then we go to the main message, why it's called effective field. And if I have time, I'll continue on to some questions of softmax and activation functions. So this is a transformer. So this is from an ICML 2023 paper from Google, and it's a parallelized version of a transformer. It's very elegant, very beautiful, because it is a linear, nonlinear, linear residual stream, as Rosanne said just now. It's adding to the previous layer. It's like a neural ODE if we use the continuous version. So it's a linear, and then nonlinear, and then linear, adding to the next to the previous layer. So, and we have wide MLP and a very narrow multi-head attention function. And the matrix of X is defined as a matrix of n by C. That is to say, we have n tokens of dimension C. And we make a little formulation here. So we formulate these matrices, these weight matrices as C by R. So it's a very good low rank projection. So we have a so-called JL lemma, or random projection, meaning that the eigenvalues of the covariance matrix concentrates near 1. So it becomes nearly like an isometry. So that's what happened in this multi-head attention. And equivalently, we simplify, we write the very wide MLP into different parts. So for the sake of convenience. And we make several further simplifications. So we consider a linear transformer. And the linear transformer is just to first forget about the activation function and the softmax function. So again, it's without loss of generality. It is a transformer that we actually use. For example, in vision, there are different variants. Say we can have ReLU, self-attention, and so on. So this is near ODE or the continuous transversion of the transformer, but this derivative is over layers, and we claim that this is somehow optimal or somehow a canonical construction from physics. So that's the next message. So we come to the next part. We define the potential field. So this is the potential field. So that is say, if we do the calculation over X star, which is the Hermitian transpose. So this is like a Schrodinger equation, because if we only consider the first part, it just equals to Ix equals X times W, and the W is a weight matrix. So the reason why we don't use a real version is that if we do so, the matrix has to be symmetric. So in many previous MLC talks and in the ice-breaking part of today's research jam said by Rosanne, there's a lot of work studying the layer-wise dynamical behavior, like a spiral version, and today's in the chat we mentioned oscillating version of this neural ODE. So we are curious about what happens in this process. So the claim for today's idea is that this V of X is somehow minimal. So it corresponds to something exists in quantum physics. So this is a linear or free or Gaussian term, and this is a quartic term. So there is something like called a 5-4 theory in quantum physics. So the dV dx star is the transformer architecture, and it's minimal because it's a quadratic term plus a quartic term, and we ignore the complexity, the next terms. So this is very straightforward, and I find it very canonical, and I'm curious about, so let me explain what is X. X is a matrix of n by c. So we have n words, n tokens, and each word is in dimensions c. So let's go back to this transformer architecture here. So xt plus 1 equals xt plus a residual stream of this thing. Yes. So the slides is there, and thank you. And so let me go ahead. Please feel free to interrupt me in the chat or in the voice message. So the message is that we try to forget about everything. We want to construct this V, this potential field, from scratch. Okay. So in this slide, I will very briefly explain why is this kind of equation canonical, and how does they connect back to quantum theory, quantum physics. So it's called either Euler-Lagrange equation, or a Schrodinger equation, or a Feynman path integral, whatever it is, and it connects back to many physically meaningful values. Say this is a path integral. This is a least action principle, and it has some Lagrange transform interpretation and symplectic form interpretation from differential geometry. And I'll skip it. Just believe me, this is something principal. This canonical term is this term is canonical. And in this idea paper, I just try to axiomize the whole thing, the transformer architecture from minimal assumptions. So I prove that this is somehow the best thing we can have as a neural network architecture. So yeah. Okay. Thank you for the reference, and I will look at it later. And basically, I make 3 assumptions on how to create this field from scratch, just as what we do from physics. So analyticity means we separate this potential into different terms, and axiom 2 is permutation symmetry from the left. That is to say, we can exchange the words of course, we want the order to be remembered, so that's why we do rotation position encoding. But as a vector, they are always exchangeable. And on the right, we have symmetry parameterized by those W's. So those are the parameter of the neural network. So we don't know what they are, and we just do it by learning. So this work is this idea is about the architecture. It has nothing to do with the actual learning stuff. And the construction says the theorem says that this form of V is something that must happen if we assume these three axioms. So yeah, I want to be clear, and I think this is a kind of very surprising thing for me, because we from this very minimal thing we just basically can uniquely define this the existence of the minimal model. So we can have this this quadratic term and quartic term, of course not odd power, because of the parity symmetry. We cannot have a potential field that depends on the first order and third order and so on. So this term associate with the non-interactive. So it's MLP only. So there's no interaction between the words, and the minimal next term we have creates interaction. So if we have a trace of twice these ways, we'll get transformers potential. So we get a layer dependent path, and that yet to be learned later. So
Hey,
just to be
Changqing,
clear. Yeah, please.
I think
Oof.
I'm gonna try to ask a question, just because
Yeah,
if
please.
we get too far in and there's no questions, then maybe people will become lost. I'm a little
Yes.
bit lost, because I guess my background in physics is not so much. Can you summarize, like, what have we concluded so far, and why is this kind of interesting, or why is it meaningful? Like, why is it surprising what you've shown?
Yes. Thank you. Great question. So the message here I try to make is that if we think of this V of X as a potential, and we somehow optimize this, we get a equation. So dx dt equals to dv dx star, of course. So that's what happened in the transformer architecture. That's the message I try to make. Because I forgot to mention this in-context learning idea, because we want something to happen within the layer and layer of the transformer. So we don't know what happened in each layer. So we desire that some in-context learning notion should happen here, because we want the layer-wise dynamic to mimic some kind of optimization process. But this
So
optimization
layer-wise dynamic, you mean the change in representation from one layer through the next block to the next layer, like what that vector is?
Yes, it's exactly what Roseanne talked about before the talks.
Okay.
And exactly some many previous MLC talks, if we remember, and basically the activation that changes layer by layer. So the dynamical variable is the activations instead of the weights. The weights is about the learning or optimization of the deep learning in the narrow sense, in the machine learning in the narrow sense. But here I'm talking about something completely different. This is layer over layer. What happens here is oscillation, or is a spiral. Spiral means a U1 group, because we have the T exponential of I theta group, and the theta is the angle, so we rotate and rotate. So that is the complex exponential. So that's why we have an ODE that converges to actually a circular behavior instead of just one point. So that is the general convergence of a general ODE instead of just one point fixed there. So we sometimes we have a rapid oscillation. That's why I find it very beautifully connects back to the quantum physics. So they have a U1 symmetry that in the standard model, and they have phase invariance. They have a minimal principle that does not allow rapid oscillation that creates the many notions in quantum physics. And I want to argue that this is what happened exactly in the emergence of the transformer architecture. Now the logic is just to train and find and tune and just wire and just we don't know how it comes from the God, and that's not yet scientific. So for a scientific theory, we have to be as logical as Euclidean's geometry. So we make minimal assumptions. We see what is the thing that we cannot reduce back. So at most we can reduce to a minimal set of axioms. So I'm trying to do that kind of axiomization and derivation. So the message here again is just to define what kind of potential. So how to just create transformer architecture from scratch. So we forget about everything. We think about in the paper I try to connect back to the bitter lesson because we want to somehow make the model minimal so that we have best flexibility for the model instead of just hand tuning everything. Just get a bitter lesson. We do a lot of work. Then the model will use prefer the simplest structure. So by the simplest structure, we want this model to be minimal. So by minimal, we use the notion of the quantum field theory. But here we have a matrix variable. So that means this x, if I draw it out, is one line is one word vector, one line is one word vector, and so on and so forth. And then this w is qk. So x star or s star is x transpose, is a Hermitian transpose. So xq dot product this xk. So this is a Curie matrix. Dot product with P matrix and so on. We have V and O here. So am I clear now? Yeah.
Somewhat more clear. Yeah. I think I'm still missing some some knowledge of physics, but I think Charles has a question as well.
Yes.
I can make a comment on this. So the earlier talk you saw, which by the way, I didn't know that he was doing this work with White Watcher. The theory behind that is based on something very similar to this. But what happens is you have the first term, which is this integral.
Yes.
You have the first term trace xwx.
Yes.
No, go back to that slide right there, right? So you have a potential function, and what you do is you write down a free energy for the model.
Yeah.
You can evaluate. So I sent a link to the paper of how to evaluate the first term in terms of what's an integral over a random matrix. You assume W is random, and it becomes something in quantum field theory called an HCIZ integral, and you can form the integral over that and evaluate it, and you get an effective field theory. And this power law exponent he was talking about is the universal critical exponent, which arises from a Wilson exact normalization group. I didn't know how to do the second term. The second term is like, to me, it looks like Wick's theorem, but the matrices are rectangular instead of square. And if they were square, I could have evaluated because you know how to do Wick's theorem. But so I just comment that I think this is fantastic. I hadn't thought about it in terms of transformers because I didn't know how to do the second term, but we talk about it in the paper and say, well, we don't know how to deal with it, so we'll just pretend it's not there. And just everything is linear. And these end up being like intercoupling terms between the layer weight matrices.
Yeah, great question. I've spent so much time thinking about the same thing.
Right.
And
so I'm sorry, go ahead.
Yeah, please,
you can evaluate the first term is fairly straightforward to evaluate. Using, as you pointed with it's basically you take an integral of a random matrix, you make an assumption over the district. In our case, we assume the random matrices are heavy-tailed power law, and then you can use a type of there's actually a paper I found. It was actually not it's from a paper in the theoretical physics literature, but it actually was published in the literature on wireless communications. So it turns out people who do wireless communications are studying like interactions between cell towers, and they have random matrix theory models to talk about the interactions between the cell towers. And there was a nice paper which explained how to evaluate the first term using the technique you showed earlier, using the inverse Legendre transform. So have you made
Okay.
progress on the second term? I mean, I'm just kind of, is this just a setup, or have you actually evaluated anything?
Okay, thanks so much for the question. So
Sure.
let's start from the second term. So if we think about a lower triangular attention score that's only associated with language model, but here for starters, we can first think about vision transformer. So that is full attention score. So after that, we can proceed. So now I try to minimize everything to build a series first, and then another thing is where a random matrix come here. So it's the W is the parameter matrix, because this is perfectly linked to the initialization of the weight matrices. So we have IID Gaussian entries. So in the next slide, I make another slide to show that if we initialize the matrix, it's a circular law, it's a circular ensemble, is and then if we calculate the covariance matrix or Wishart matrix, it twists to the real line. So the learning makes the eigenvalues go away from this random ensemble, and that's where signal and power law happens here. So in the previous talk, we discussed what happened beyond the bulk distribution. So that's how we detected the signal, and this is the connection. So I try to make, and this X here is the state value. It's the after you multiply your state, is the thing that adds to your is the activation value. So yeah. I just please. Yeah.
So typically in a field theory, you would integrate out over X, right? You would assume something like X is a Gaussian random field, and then you would integrate out the variables. Is that what you're doing here, or something different?
I also look into something that people, they call it neurotangent kernel, to analyze, to attack what happened in treating the state, of course, as a statistically formulated distribution like Gaussian and so on. But I'm not doing this thing. I'm claiming something stronger. So I'm not thinking of the states as a distribution, but just want to formulate what exactly happened. So it's a strong condition. So before, if we think about the neurotangent kernel, it's a statistical tool to analyze the states, what happened. But here I'm trying to build the architecture. So I think
I just had a comment. I know nothing about neurotangent kernel. I only know quantum field theory and statistical mechanics. So I know what you're doing. I don't know what they're doing.
Okay.
So that's what I'm saying. How do you evaluate? So you have a technique for evaluating it yet? I'm trying to. I mean, do you integrate out over W? Is that the idea?
In fact, no, because
Okay.
I'm not integrating over W. W here is totally unknown. It's something we set here. So if we don't look at the second term, we only have the first term. It's just a linear Schrodinger equation. So this W is the parameters later to be learned by backpropagation. So we have nothing. We are totally orthogonal to that thing. So it's just a unknown variable, and we set it just to decide what our architecture should look like. So this W is if we go the previous slide is W in times W out transpose. So a lot of narrow matrices composes a very wide network, and then this together is the W is a weight matrix. So this is what happened in the network. So and here the analogy comes here. So if we write into this formulation, we can write everything into the very elegant equation. So QK is input hierarchy parameters, and V as well, and O is output parameters. So this is another W matrix. This is another W matrix. We just do something like the low rank reparametrization on the W. So as our assumption goes. So yeah. So the argument is that here what happened is that this is something canonical. So the first term, of course, is a linear term. We are familiar with it. We know how to deal with it, as you said. This is what happened in the Schrodinger equation, linear Schrodinger equation. And this nonlinear term is the minimal, is the first term that creates interaction. So after that, we just have the linear transformer architecture, and that's all. We don't analyze, we don't integrate over anything. And I think I try to minimize everything to make the message better explained. Yeah, I'm not a physicist, and I'm trying to learn these things along the way.
That might make it harder.
Yeah,
Well,
yeah, please.
Go ahead.
Yeah, please, if you have a question.
I was just going to comment, if you go back, when we talk about W, one of the things that we assumed, we realized early on, is that, so we treat W in the Weight Watcher theory, we treat it as an experimental observable, right? So you measure W from experiment, and those then become parameters that go into the theory. And what we realized a long time ago is that the W lives in a different universality class than the universality class of Gaussian random matrices. And this will impact the theory, because if you try to build a perturbative theory starting with the Gaussian universality class, it's not clear to me that you can reach the heavy-tailed class, because you do go through this renormalization group transformation. So that's why we start, so I'm not sure how you would get to the end if you start in a different universality class, how you would get to the final result. But I just going to comment on that. That's sort of the approach. I realize that W is just something you measure as it goes. So the theory is more, and what you end up is you end up renormalizing. So the parameters in W look something like, if you're not a physicist, if you're a physicist, you would say it looks something like a renormalized self-energy. So, but anyway, just a comment on thinking of ways to approach it.
Okay. So you should be writing the Weight Watcher paper.
I sent the link in the chat.
Okay, thank you. I'll read it later. And here, maybe a difference is that this W is separated into two. It's a input layer and output layer. So if we analyze one input layer, of course we can take a freshly learned pre-trained model and analyze its say power law
you can actually do this with the tool. Like Weight Watcher will actually analyze the intercouplings between the layers, but because I didn't know how to evaluate that second term, I just never use it. I don't know what to do with it.
Yes.
But
yes,
I think
that
like we knew we had to do this. We have no idea how to evaluate it.
Yeah, that makes a great connection here, because with this formulation, we find that if we know that this is input-output layer combined, and then we know this is this interaction is associated with two matrices, and then this is QK and this is VO, and then the analogy here is that for the first term we have a linear model is okay. Of course we will have ReLU that makes things complicated, but this is for a linear transformer, and of course a softmax will make it more complicated. But the analogy here is that what happened in this dot product is a symmetric formulation of Curie and key matrices. So by symmetric, we don't mean empirically, because of course empirically they have a more important for the latter matrix than the previous matrices. So but mathematically they are a dot product, so they are mathematically symmetric. So if we write Q and K together, this is this is associated with the first dot product. This again, this VNO is on another self dot product, and again, I think this work maybe will compensate or complete the Weight Watcher paper, because as I said, this is we don't know anything about. We just set the weight matrices as unknown variable, so we don't know. We don't assume anything. It's just like Claude Shannon's paper saying the information theory is not about information. It's just about the architecture of information, or the quantity about information. So yeah, to make clear, I just want to connect to the spectral distribution, but we don't actually touch that yet. But the reason I still want to emphasize this idea is that this kind of formulation of V again is something we can only have just by assuming a couple of axioms. We can only have this minimal architecture. So we as you said, this is a very good comment. Now we have a full attention matrix, and we have a linear attention matrix, attention without softmax. And I have some slides for the softmax. If you care about the softmax, it's here. We can have a entropic regularized energy to recover the softmax, or we can say it's log sum exponential potential. So it's how we create the softmax, and also for the activation function. There's a bunch of slides for that. Yeah, and yeah, I think this is the entire message here. I think if you have questions, please go ahead.
Awesome. Thanks for the presentation.
Yeah. If not, I still have
any questions?
Just the other comment I'll make is that when you formulate it, you're formulating in terms of input. The W is the input-output coupling, right?
Yes.
So the way I got around this is that instead think about student-teacher. So I have a teacher and I have a student, and the student is mimicking the teacher. And there's an old paper from the 90s that shows you can compute the generalization accuracy of a model by looking at the integrated overlap of the student-teacher. So rather than that's how we are able to evaluate the integral. So we know what the teacher is because you measure it, and the students are all possible students that overlap with the teacher. So it's a slightly different formulation, but we get the same. I mean, it's the same setup though. So it's very, very interesting. Can you go back to the slide you just showed? No. Go forward.
Forward.
That one. Okay, thanks. I just want to take a look at it a little more carefully. Thank you. Yes.
Yeah. If you have that reference, could you
sure. Yeah. It's in the, and also I'll send you my blog because the blog is the blog's a little shorter, not 150 pages.
So I think I'm over time. I'm sorry, but I have I'm flexible about the time frame, and I have a lot of other slides, and maybe I'll just play the thank you slides. Yeah.
Perfect. Let's all take a moment to thank Changqing and all the other presenters. I'm going to stop the recording, and we can continue discussion after.